everyone. Now let's continue from our next example. So, we will have an example which asks us to determine the Fourier transform of a delta Dirac function. What do we do in this case? Again, we will apply our formula and we will just write this formula that we were using in the previous lesson. And we will write, instead of x of t, we will write delta function. So it will be like this. Now, have you noticed something? When delta function is not 0, it is at the points when t equals 0, then delta function equals 1, right? And when let me write it here 0, here 1. When t is 0, this value over here becomes 1. So having a delta function 1 and this one 1, we will get 1 in return. But in the integral, it says to sum up all the values from negative infinity to positive infinity, right? Which means we will add up also the other values. However, as the delta function will equal to 0 in other values, in here it will equal to 0, anything multiplied with 0 will give us 0. So we will basically sum up all the zeros in here. Eventually, our answer will be 1. Now, let's move on to our next example. Example numbered 4.4 in the book. Now, our example says that we have a function, piecewise function as shown, and it needs us to find the Fourier transform of this series. As we can see, this function actually tells us that the function equals to 1 until it reaches a value of capital T1 and here negative T1, and after a while when it reaches T1 it becomes 0 as a value. So it's a similar type of rectangular function, but it has just one loop. So let us find the Fourier transform series. Now I will directly apply the formula here. We will apply this formula over here, as always. And let me write. Since our function is 0 in other places, we can directly write, instead of minus infinity to plus infinity, we can write from minus t1 until t1. And then our function itself is what? Here we have 1, as it is written here, is 1. So we were writing 1 times e to the power of minus j w t dt, right? And then let me take this integral. It will come off as this over minus jw, because we are integrating with respect to t. And then from minus t1 to capital T1. So expanding this, we will get this expression. And what we can do in here is to multiply both the numerator and the denominator with 2j. So if I multiply like this, what will happen? 1j will be cancelled out with this one, and we will have an expression like this, times let me write it over here like this. So I want to ask you something. What is this equal to? This is equal to the sine JWT1, right? So this was a trick to actually simplify this equation. So eventually we will have, and I also need to emphasize, we will multiply both sides with negative. So let me, we will basically put this negative inside the parentheses, so we will write it here, sorry. Eventually we will have 2 sine JWT1 over W. And here is our end of this question. Now let us try another question, another example. This time it asks us another function which has an exponential value. So as we can see, we have a function here, x of t, and we are asked to find the Fourier transform version. So let me quickly write our formula. And now apply it to the question. And now we will write what is small xt. Okay, so as we know that this unit step function, what is it? It is 0, and then after 0 it takes the value of 1. So it is exactly equal to, so basically when in the from negative infinity until 0, whatever we multiply to it, it will give us 0. So we can basically delete this minus infinity and write 0 instead of it, because it will in any case give us 0 in any situation. So we are not required to compute that part, as it will give us 0. So let us continue. We can take out these two together. And we can integrate it with respect to t, and it will give us a plus wjt over minus a plus wj from t equals 0 to t equals infinity. And this is, let me take the denominator out. Here we have again the same boundary conditions. And if t equals infinity, it will give us 0. Let me write it more openly. Here, if we write in this one, t equals infinity, it will give us 0, right? This one will go to 0. And here, if we write 0, then if here we multiply it with 0, then it will give us we multiplied it, so it will give us 1, right? Eventually when we equate this, when we do this equation, we will take this result. And here is the end of this question. Now let us apply another question which asks us to apply the different conjugation or other properties that we have learned previously. So let us see what this example is trying to make us figure out. So here we are given a Fourier transform and we are asked for the function itself. And so how can we do this? We can notice a similarity with the previous question. So in the previous question we actually figured out that if our function is e to the power of any constant, let me write it as a subscript I times t ut, then the Fourier transform of it is given as 1 over a plus j w, right? Now, here we are given the Fourier transform, and which is this one, and we are asked for the function itself. So here we can see a similarity. What is the difference? Here, this one, the second Fourier transform is multiplied with alpha I and then is also summed up over a period of I, right? And as we know, the Fourier transform has first linearity property. That's why if we sum up the Fourier transform or the function, we will sum up the Fourier transform, and it's true also vice versa. So we will sum up also the function itself. There will be a sum, there will be a sigma also in the function itself, alright? And also, due to linearity property, if we are going to multiply each and every item, Fourier transformed item, in Fourier transform version, we will multiply each and every one of them also in the function itself. So here we are getting somewhere. We had the function, and as we just explained, the function was this. We will multiply each one and every one of them with alpha due to linearity property, and also due to the same property, we will sum them up over the period I. And this one will give us our function. And our example is finished now. As we can see, we could find the function out from the Fourier transformed series by using a linearity property. Now let me mention about another topic, convergence of Fourier transforms. Convergence means that, let me write it here, convergence means that the function f(x) of t, let me write it such as this, which is an estimation of x, let's say. If this formula is a valid representation of the original signal xt, then we can say that xt is convergent. Now let us look at the sufficient conditions. Condition number 1. xt has finite energy. Let me write it. So, in other words, we can say its square is integrable. I will show you what I mean by this. If we integrate from minus infinity to plus infinity, the small function xt, and we square it, and if it is smaller than infinity, so we can compute it, then we can say the Fourier transform of xt exists and converges. Now let us move on to the second alternative solution. Second alternative condition. If xt is absolutely integrable, then the Fourier transform of xt exists and converges. Let me write it down real quick. Is absolutely integrable. So what I mean is, when we integrate from minus infinity to infinity, absolutely means in absolute value, it is smaller than infinity, and then the Fourier transform of xt exists and converges. That's it. Now let's move on our next example. Example asks us to determine the Fourier transform of the given functions. So our first example is this. What are we going to do? We are simply going to apply our good old formula. And once we do this, we will have this result. And then we need to, as always, make use of this step function, and we are going to integrate from 0 to infinity. And we will take the integral, and let me take into parentheses all the stuff. And eventually let's integrate. And then write this part separately. And then eventually if we write here infinity, it will give us 0. And if we write here 0, it will give us 1. So our final answer will be 1 over 2 plus jw. That's it. That's easy, right? Now we have done a plenty of questions. Now let us continue with different properties. And we will start with time shift property. Properties of Fourier transform. 1. Time shift property. What this property tells us is that the Fourier transform of the function t minus t1, if we shift this function by t0, we will take the Fourier transform of xt, and we will just multiply it with e to the power of minus jwt0. Okay? Now let me show you the proof of this. And here we have our function. In order to compute the Fourier transform series, we will going to use this formula. Let me write it to this corner so we can take reference. So when we apply this, what do we have? 1 over 2 pi from minus infinity to plus infinity. We will have e to the power of j w. Instead of t, we will write t minus t naught dw. And then if I open up this this one, what do we have? So as we can notice, this part is exactly the Fourier transform of the previous function x of t. So here we can write it like this. And this part only will come out, and it will be the coefficient of our Fourier transform. Eventually, we will have and now let's move on to the next property, which is conjugation and conjugate symmetry. Now, what does this property tell us? So it tells us that if we have a function xt and the Fourier transform is capital xjw, then x star t, the Fourier transform of x star t, will be the conjugate of the Fourier transform and the minus. We put minus also inside. So it tells us this two relations. And let me give you the proof of this property. X star jw equals now let me write x star minus jw equals the conjugate value of this property over here, this and let me write it here like this. Why is that so? Because we actually knew that our previous formula was this. So if we are going to write minus in here, we multiply minus with here, so minus minus, we get plus in here. That is the reason why. And we are going to take the conjugate of both sides. This is what we are doing in here. And taking the conjugate, what are we going to do? We are basically, let me copy and paste it over here. We are taking the conjugate of this, and then as you remember the conjugate property, as we have this, the conjugate, we will have the minus of this one over here. That is why we are going to put minus also in here. As a result, what do we observe is that this was actually the same as this part, our original formula, without the minus. And then it is just the function has just the only difference is its being the conjugate. Eventually, we can simply write x conjugate t instead of all this expression. Eventually, we saw that x star t, x conjugate t, is equal to Fourier transform conjugate and minus jw inside. And this was the proof. As a result, we can make a quick summary, and we can say if xt is real, we can say that the Fourier transform of x star t is equal to this expression. That's it. And now let's move on to the next property, which is differentiation and integration property. What this property tells us is basically if we take the derivative of the function x, then the Fourier transform is j times w times x jw. So eventually the differentiation in time domain will give us something with in the frequency domain. And let me prove this for you. So we have this original formula as always, right? 2 pi from negative infinity to plus infinity. And then what do we have? If we were going to integrate this expression, what will we have? This expression, right? And then as we noticed, this was already our previous expression. So this is already equal to, this is already equal to our function. And the only difference is that we are going to multiply it with jw. Therefore, we can sum it up. Let me write this here. Therefore, this one is actually equal to, as a result, we can see that we actually what did we do? We connected the time domain with frequency domain. Now that we know the derivation, we can also write the integration. However, I will not make the proof. I will just write integration and give you the result because it is long. And from minus infinity to infinity, x tau d tau has the Fourier transform as such: 1 over jw plus pi times x function in the at time 0 times delta function at omega. Here the impulse term reflects the DC or average value that can result from integration. It can result from integration, that's right. And then let's move on to the next property, which is time and frequency scaling. And this one tells us that if function xt has Fourier transform xjw, then xat has Fourier transform 1 over absolute value of a, and then times x, the Fourier transform jw over a. The absolute value here is important because we actually have, we can also write this in this term, in this way, at 1 over a from minus infinity to plus infinity x tau if a is bigger than 0. However, the minus 1 over a times the same expression is true if a is smaller than 0. So we should pay attention to the absolute value. And here are our properties. Thank you for listening. Have a nice day.